Okay guys, welcome to video 2. So as a refresher, the problem that we're working on is an equimolar mixture of ethanol and air at 75 degrees Celsius flowing at 200 standard liters per minute is fed into a condenser operating at 20 degrees Celsius in 1 atmosphere. So in video 1 or part A, we determined the rate of condensation of ethanol in moles per second. And if you haven't already watched video 1, there should be a link popping up here and a link in the description. So what we found in video 1 is that the rate of condensation of ethanol is 0.07 moles per second. Okay, and so in part B, we're going to determine the rate of heat removed from the system in kilowatts. And so just like in video 1, I recommend pausing the video here, attempting the problem yourself, and then the rest of the video, we'll work out the problem together. See you soon. All right, guys, let's get into this energy balance. Okay, so if you guys remember from last video, we solved for the molar flow rates of the vapor and liquid streams. So we're going to put this all together in the energy balance. But first, we need to draw our table. And so a table is a good way to keep track of all of your molar flow rates and all of the enthalpies that you need to solve for in your energy balance. So let's just go ahead and complete the top part of the table and then start filling out the species. And so in the energy balance and you're filling out your table, you need to include the species, the phase that the species is in, and the temperature that the species is in, because we need to account for both latent and sensible heat changes. So in our problem, you see we have ethanol vapor at 75 degrees Celsius, which is entering into the system. We have ethanol vapor at 20 degrees Celsius, which is leaving an outlet vapor stream. We have ethanol liquid at 20 degrees Celsius, which is leaving in the liquid ethanol stream. We have air vapor or air gas at 75 degrees Celsius, which is entering into the system in the inlet stream. And then we have air vapor at 20 degrees Celsius, which is leaving in the vapor stream. So now let's choose a reference state. So a convenient reference state, especially for this problem, and since we know so much about the inlet stream, is the inlet stream and the conditions of the inlet stream. So for this problem, convenient reference state is vapor, phase. Remember, a reference state is going to be phase and temperature. We could also include pressure. However, the condenser is operating at 1 atmosphere, and we are assuming an ideal gas in this system here, and we're also assuming that it's at saturation. If we assume that it's at saturation at 75 degrees Celsius, then the pressure is not going to be at 1 atmosphere. We need to solve for that. You should convince yourself that if you were to account for the energy change of the inlet stream going from 0.9 to 1 atmosphere, it would be so low compared to the sensible and latent heat changes. You can essentially call the pressure change very negligible compared to those. Okay, so now let's start filling out our table with information. So we're going to begin by completing the inlet side of the system. So we're going to start with ethanol vapor. It's entering in at 4.46 moles per minute. And because we have a reference state that we're going to be integrating over, the enthalpy N is 0 because we're at the reference state. So there's no energy exchange at that point. Okay, so there's no ethanol vapor at 20 degrees Celsius or ethanol liquid at 20 degrees Celsius entering in the condenser. The next stream that we have information about in the inlet is air vapor at 75 degrees Celsius, which is entering in at 4.46 moles per minute. And the enthalpy, because it's again at reference state vapor at 75 degrees Celsius, is 0 kilojoules per mole. There's no air vapor entering into the condenser at 20 degrees Celsius, so we're not going to account for that. Okay, so now let's complete the outlet part of our table. So ethanol vapor at 75 degrees Celsius is not leaving in the outlet stream. Ethanol vapor at 20 degrees Celsius, we calculated is 0.27 moles per minute. And this is what we're labeling as H1. And we are going to have an enthalpy there because we're integrating from 75 to 20 degrees Celsius. Okay, and then the ethanol liquid is leaving the stream at 4.19 moles per minute. Enthalpy, we're going to label as H2. And then the out of vapor air is 4.46 moles per minute. And so we're going to call the enthalpy that we're going to solve for here as H3. Okay, so now we're going to start with our process paths. The reason why they call it process path is because we're actually now going to solve for the sensible and latent heat changes. So we initially have ethanol vapor, 75 degrees Celsius, and we're going to go ahead and assume that our state that we're starting with is ethanol vapor, 75 degrees Celsius at 1 atmosphere. And we're going to take this ethanol stream to ethanol vapor in the outlet stream at 20 degrees Celsius and 1 atmosphere. Okay, so now the delta H1 is the integral of Cp, the heat capacity dt, from 75 degrees Celsius to 20 degrees Celsius. And so ultimately, because there's zeroth order temperature dependence in the heat capacity that we were given, it ends up being Cp delta T. Okay, so now we want to look at ethanol vapor going to ethanol liquid at 20 degrees Celsius. So this process path is going to be a hypothetical process path. This is not actually what is occurring, but this is what we need to do to be able to accurately capture what is happening to the energy of the system. Okay, and so because the book that I got my latent heat of vaporization from has the boiling point of ethanol at 78.5 degrees Celsius, we first need to take the ethanol vapor stream at 75 degrees Celsius in 1 atmosphere, and we need to increase the energy through a sensible heat change. We need to increase its ethanol vapor at 78.5 degrees Celsius. Okay, and then once at 75 degrees Celsius, we're going to remove enough energy from the system, and we're going to change the phase. We're going to have a latent heat change, and we're going to convert the ethanol to liquid at 78.5 degrees Celsius. Now we can, of course, first write down the latent heat of vaporization, and it's going to be negative in this case because we're removing energy from the system. And now that we have ethanol liquid at 78.5 degrees Celsius in 1 atmosphere, we can take and perform a sensible heat change from 78.5 degrees Celsius down to 20 degrees Celsius. Okay, and so this is a hypothetical process path because this is not actually what is happening, but this is what we need for the sake of problem solving. Okay, so now we have our process path here. Now we need to start solving for the individual streams. So we have delta H2 equals the integral of Cp dt from 75 to 78.5 degrees Celsius. And now we're adding the latent heat of vaporization of ethanol. Then we're going to add another integral from 78.5 to 20 degrees Celsius. Okay, so putting this all together, because of the zeroth order temperature dependence, we have Cp ethanol vapor delta T plus the negative latent heat of vaporization plus Cp ethanol liquid times delta T. Okay, so let's fill out our process paths with the sensible heat changes. And then let's include it by the table. Okay, so now let's look at the air stream, and let's look at the air vapor at 75 degrees Celsius in 1 atmosphere. All that's happening here is just a sensible heat change. So we're going from 75 degrees Celsius to air vapor at 20 degrees Celsius in 1 atmosphere. Very straightforward. So delta H3 equals the integral from 75 degrees Celsius to 20 degrees Celsius of Cp air vapor dt, which equals Cp air vapor delta T. Okay, so now we can calculate the rate of heat leaving the condenser equals delta H. And so this, remember, this delta H that Q equals is not the specific enthalpy, rather the total enthalpy. And so how we get the total enthalpy from the specific enthalpy is we multiply by the molar flow rate. So it's the sum of the molar flow rate out of all the streams times the enthalpy of all the streams and the species in the stream. So we're actually summing over the species, and the species outlet are also including the phases as well. And then we're subtracting the molar flow rate in times the specific enthalpy in of the streams coming in, or the species coming in. And so there's no energy coming into the system because of how we chose the reference state. Okay, so let's put this all together. So we have the molar flow rate of ethanol vapor times the heat capacity of ethanol vapor times the delta T plus the heat capacity of ethanol vapor delta T plus the negative latent heat of vaporization of ethanol plus the heat capacity of ethanol liquid times delta T. All of this multiplied by the molar flow rate of ethanol liquid plus the heat capacity of air vapor times delta T times the molar flow rate of air vapor is the rate of heat removed from the system in kilowatts. However, we can make this a little more compact using the enthalpies. And so remember, this is the specific enthalpy, and we multiply it by the molar flow rate to be able to get the rate of heat removed from the system. Okay, so now let's begin adding our known information and all the information that we solved for. So remember, we were given the heat capacities in initial problem statement, so let's go ahead and write those down. Let's go ahead and write the molar flow rates that we solved for. So we have air vapor, ethanol vapor, and ethanol liquid streams. And let's also write down the latent heat of vaporization. Now we can begin solving for the temperature changes. And so remember, the light blue delta T represents the inlet temperature changes. And so we're going from 75 degrees Celsius to 20 degrees Celsius, and the integration balance so is B minus A. That's how we get negative 55 degrees Celsius. The green, remember, this was a hypothetical process path going up to the boiling point because our latent heat of vaporization is at 78.5 degrees Celsius. And then we have the navy delta T, which is also a part of the hypothetical process path going from the boiling point in the liquid phase to 20 degrees Celsius. Okay, so I recommend pausing the video here, inserting the parameters and the information that we solved for into the equation above, and compare what I get. Okay, so if you're just coming back after inserting all the parameters and variables that we solved for, what I got was negative 192.8 kilojoules per minute, which is approximately equal to negative 3.2 kilowatts is the rate of heat removed from the system. And so to get kilowatts, you just divide by 60 seconds in 1 minute, and then you get kilojoules per second, or kilowatts. So for part B, the rate of heat removed from the system in kilowatts is approximately negative 3.2 kilowatts. Okay, guys, I really appreciate you watching this two-part series of solving this condenser problem. I hope this has really helped your chemical engineering adventures. Please like, comment, share, and subscribe. I'll see you in the next video.